Let's come back to that example from our previous video, and let's show that instead of doing this convolution in the time domain, we could have done multiplication in the frequency domain. And so remember, the two cases we talked about where you want to avoid working in the frequency domain is maybe this expression is really complicated and it's difficult to inverse Laplace transform, so that's one case. Our second case was maybe these x of t and h of t components don't have an explicit transform. So maybe there's some experimental data that we can't take the Laplace transform of, in which case we want to do our graphical approach. But of course in this case we can see our x of t and h of t, which I've copied again here, are relatively simple, so we don't have that issue. We can't know about this x of s, h of s until we actually find our Laplace transform of these functions. But knowing that these are pretty simple functions in time, they should be pretty simple in frequency as well. So let's start by writing our equations in time for these two plots here. So for both of these, we can do a combination of step functions. So we can say that our h of t is actually equal to 2 times our unit step function minus 2 times our unit step function shifted by 1. And so what this is basically saying is we have a component that turns on at t equals 0, and we have a component that is turning on, but then it's being subtracted at t equals 1. And so that's how we could write an expression for this function h. If we take the Laplace transform then, we could find our h of s, and so using our known pairs and properties, we could say this h of s is equal to 2 over s minus 2e to the minus s divided by s. So similar approach for our x of t. In time, we can say this x of t is equal to our unit step function shifted by 1 minus our unit step function shifted by 3. And so that's our expression in time for our x of t. If we take the Laplace transform, we can find that our x of s, again, just using our known properties and our tables, we can say x of s is equal to e to the minus s over s minus e to the minus 3s over s. So what we want to do now, of course, is take the product of those two time domain or frequency domain functions. So we can say h of s times x of s. And so remember, the order doesn't matter because of our commutative property. And so this is going to be equal to, so let me factor out a couple common terms. So we see all of these terms have an s, and we also have this 2 term in our h. So what I can do then is I can factor out a 2 over s squared, and then our remaining terms for our h are 1 minus e to the minus s, and the remaining term in our x of s is e to the minus s minus e to the minus 3s. So multiplying that out, we have this 2 over s squared out front still, and then we have an e to the minus s minus e to the minus 3s minus e to the minus 2s, and then minus e to the minus 4s. And so I've just used the fact that when you multiply exponents, you add the exponents together. So what we can do now is we want to inverse Laplace transform this, because remember, this is equal to the Laplace transform of our convolution. So what we want to do is take the inverse Laplace transform, and so we can pretty easily do this using our time shift property. But again, we're just relying on our tables because we already have this sort of in simple form. We don't have to use partial fraction expansion or anything like that. So using this time shift property, we can say that the inverse Laplace transform of our x of s times h of s is equal to, so we have a factor of 2 out front, and then we're going to have t minus 1, that quantity multiplied by u of t minus 1, so that's a shifted step function, minus the quantity of t minus 3 times u of t minus 3, minus quantity of t minus 2 times u of t minus 2. So we see a lot of shifted step functions. And then finally, we're going to have plus t minus 4 times u of t minus 4. Okay, so at first glance, it's not obvious that this equals the convolution because we know that this should equal the convolution of h of t and x of t. And again, the order of this doesn't matter. We could say this equals the convolution of x of t and h of t. But at first glance, this doesn't look familiar to what we saw from the from our previous video. So let's take a closer look. So let's consider sort of our different times here. So for t less than or equal to 1, let's consider what our inverse Laplace transform, and I'm just going to put a dot to indicate that we have this stuff in there, just so I don't have to write it each time. So for t less than 1, none of these step functions are going to be quote-unquote turned on. So we're still in the region where they're equal to 0. And so what that means is that consequently our overall inverse Laplace transform will just be 0. So now let's say we want to look at t greater than or equal to 1, but less than 2. So looking at this inverse Laplace transform, now we have turned on this function. So we have a 1 for this, but we still have zeros for the other step functions. So we have a t minus 1 term, but that t minus 1 is multiplied by the 2 out front. So we're going to get a 2t minus 2. Okay, so we can see the next sort of point of interest is we still have this turned on, and then at 2, we're going to have this one turning on as well. So we can say, let's look at t greater than 2 and less than 3, so we're not yet turning on that third shifted step function. So in this case, our inverse Laplace transform, so we have the 2t minus 2 from our first step function, our u of t minus 1 here. And now as this u of t minus 2 turns on, we get this t minus 2 term coming in. But again, that's multiplied by 2. So what that looks like is we have minus 2t minus 4. And so what we can see here is the 2t is going to cancel out, and we'll have negative 2 minus a negative 4, which gives us 2. So moving on, if we then look at the range for t between 3 and 4, we have the inverse Laplace transform is equal to, so now from our previous part, we could write out each of those things, or we could just start with 2. So let's say we know from our previous one we had 2, for instance. And now we have our shifted step function u of t minus 3 cutting in. So we have this t minus 3 term, but again, that's being multiplied by 2. So we're going to have minus 2t minus 6. And so what this is going to give us is, of course, we're going to have a minus 2t and then 2. And so I must have a typo here. So we have 2. Oh no, so 2 minus a negative 6 is going to give us our plus 8. Okay, so then our final time frame that we want to consider is our t greater than 4. And so for our t greater than 4, we're going to have that last shifted step function cutting in. So we have this turning on finally. So now all of them are on. So from the combination of the previous 3, we know we had a negative 2t plus 8. And again, we could write out each of these terms every time. We could write out 1, 2, 3. But we already know from summing those, we get negative 2t plus 8. So with this u of t minus 4, we have a t minus 4 cutting in, but again, it's multiplied by this 2 out front. So what we have is plus 2t minus 8. And so of course what we can see here is that our 2t's are going to cancel out, and our 8's are going to cancel out, and we're left with just 0. So if we go back and we compare, what we would see is that these are the expressions we had for our related time intervals over here. So as we would expect, we get the same thing as we did with our graphical convolution approach.